Okay, so this is a review of homework 2, which is all about refutation trees, or what are sometimes called truth trees, or just trees. At the level of propositional logic, this is a algorithmic method. It's actually an effective procedure for determining whether an argument is valid or invalid, and also for determining whether individual propositions are contradictory or tautologous or contingent. So I'm going to be assuming general familiarity with the method and the rules, since that's been given to you in the videos in this section. But I'll just begin by looking briefly at the tree rules, a summary here, which is at the bottom of the Canvas module. So the first one is the rule for double negation. It tells you that not A gets decomposed to A. In other words, you just remove the two double negations. And what this is representing and what it's telling us, and when this is the case with all the tree rules, is that there's only one condition under which not A is true, and that's when A is true. Now, if you go to A and B, that gets decomposed as A over B, so that essentially we can draw a straight line through A and B. And what that's telling us is that the only time that A and B is true is when both A and B is true. By the way, you'll have noticed that I've adopted here, and will in this module, the convention of dropping the outermost brackets. So these aren't written as true woofs. We drop the outermost brackets when it's convenient to do so, but this actually introduces an issue, which I'll be careful to indicate later. At any rate, the important thing to understand is that these tree rules are being read right off the truth table. So if we think about A and B, you'll remember that the truth table for A and B tells us that the only time A and B is true is when they are both true. On the other hand, the truth table for A or B tells us that A or B is true when either A or B is true. And so this gives us a branching rule. The branch is telling us that these are the two cases when A or B is true. Either A is true or B is true. Now, you might say, well, the truth table says that it's also true when they're both true. There's 3 lines, not just 2 lines. And that's right, but that's actually covered here. Because if A or B is true when just A is true, then it has to be true when both A and B are true. Now, you'll remember that the conditional is just a version of the disjunction. And you'll hopefully remember that if A then B is logically equivalent to not A or B, and that's why we have this rule. So since it's equivalent to the disjunction, you would want to expect that it's a branching rule, and this tells us that if A then B is true, when not A is true, or when B is true. And then you'll also remember that A if and only if B is equivalent to the conjunction of if A then B and if B then A. But what this rule is actually capturing more explicitly is that the biconditional A if and only if B is true only in 2 cases: when both A and B is true, or when they're both false. Okay, so that's, again, just read straight off the truth table. So a different version of this rule might write A and B on the left-hand side here as an actual conjunction, and then applying the rule to the conjunction similarly on the right. But so we take sort of 2 steps here and just immediately put A and B, or not A and not B, vertically. So on the right-hand column, you have rules involving the negation of the corresponding non-negated formulas on the left. So it's not the case that A and B decomposes to not A or not B. It's not the case that A or B decomposes to not A and not B. It's not the case that if A then B decomposes to A and not B. And it's not the case that A, if and only if B, decomposes to A and not B and not A and B. Okay? So these are things you have to memorize. It's not very difficult to memorize them. And my advice is don't just memorize them by rote, but really make them make sense to you, because they do make sense. If you've memorized the truth tables, they make eminent sense, but they also make intuitive sense as well. And when you're applying these rules, don't mess around with the order. Make sure, for example, that with the biconditionals, you decompose them in exactly this order. Okay, the last thing I'll mention is that anytime you apply a rule, you always put a check on the left-hand side of the formula that you're decomposing. That check tells you that you are done with this, that you no longer need to pay any attention to it. So while I'm doing the homework, I'll make some sort of, random observations about the conventions for decomposing these trees, but I'm going to assume general familiarity with the method, or this would turn into a very long homework review. Okay, so the first column of homework problems is the evaluation of arguments for whether they are valid or invalid. So of course it's very important to remember what a valid argument is. A valid argument is one in which it's impossible for the premises to be true and the conclusion to be false. Now, another way of saying this is that if the premises are true, then the conclusion must be true. But this mode of impossibility, I think, is really important and helps us to understand the truth tree method. So what we're looking at here is an argument with only one premise, R if and only if it's not the case that K if and only if S, and there is always only one conclusion. In this case, it's not the case that R and K and S. So the question we're trying to ask is this a valid argument? Another way of asking this is, does the premise imply the conclusion? Well, as I just said, if this is a valid argument, then it's impossible for the premise to be true and the conclusion to be false. So the tree method is just a way of determining whether or not that possibility exists. So we ask ourselves, is it possible for the premise to be true and the conclusion to be false? And when we ask that question, we basically say, well, let's see. What happens if we assert the truth of the premise and the falsity of the conclusion? If we assert the truth of the premise and the falsity of the conclusion, if that's impossible, that should result in a contradiction. And so what the tree method tells us to do is to write the premise on top. So R if and only if it's not the case that K if and only if S, and then write the falsity of the conclusion on the bottom. So what that means is you need to negate the conclusion, right? Remember, the negation is a truth value flipper. So in this case, and again, this shows you why it's so important to be able to identify the main operator. In this case, the main operator is the negation. I'm talking about the conclusion now. The main operator is the negation, so we can assert the falsity of the conclusion by simply ripping the negation off. So we just write R and K and S. By the way, I make my ands like this, and therefore you can too. Don't introduce any other modifications on these operators, so all the rest of them are pretty straightforward and easy to write. Okay, so we've just constructed this as a list, right, where the conclusion is on the bottom. And that's really all an argument is. An argument is just a list of propositions where one of them is identified as the conclusion. And when we ask whether it's a valid argument, again, we're asking whether it's possible for the premise to be true and the conclusion false. If we end up concluding that it's impossible, really what we're saying is that the conclusion is somehow already asserted by the premise or premises, right? That's the only way it can be impossible. So if it's impossible for the premise to be true and the conclusion to be false, that means that somehow the premise or premises contains the conclusion. And because of that, if we assert the premises and the falsity, the negation of the conclusion, then we should get a contradiction, a logical contradiction. And that's the whole basis of the tree method. Okay? So now all we do is just apply the rules, and the prudential rule, and by prudential I mean it's not absolutely required, but you are foolish not to use it, is to always, or at least almost always, decompose the non-branching formulas first. Okay? So in order to do this, as I said before, you have to understand what the main operator is. Okay? So here the main operator is a conjunction. Here the main operator is a biconditional. The conjunction is a non-branching rule. So the first thing I'm going to do here is write R, and then I'm going to write K and S. Okay? And immediately after having done this, I'm going to make a check which discharges that formula, which means that I never need to go back and look at it again. Okay, now K and S is a conjunction, so I'm going to go ahead and operate on that one. And again, discharge. And now at this point, I'd look to see if there's any contradiction. Now, it's very important always to understand what a contradiction is. A contradiction is some formula, A, and its negation, not A. That's the only thing that a contradiction is. Okay, so for example, if you have P then Q, right, the only thing that will constitute a contradiction of if P then Q is it's not the case that if P then Q, right? This whole thing negated. And that's why it's super duper important to be careful when you are indulging this opportunity to drop the outermost brackets. Because if you do drop the outermost brackets in the way that I've done here was if P then Q, then if you're going to negate that formula, you have to put them back on. If you simply put a negation on if P then Q, you haven't negated the whole formula, you've only negated P. Okay, so it's a very, very common rookie mistake in doing trees and also later on when we do proofs in natural deduction. Okay, so now we go back to the biconditional and we decompose the biconditional. This is the main the first biconditional is the main operator, and that's a branching rule, right? So we go to R and not the case that K if and only if S. And on this side we write not R and not K if and only if S. And yes, it does have to be not. You can't simply cut to K if and only if S, even though it's logically equivalent, because the rule requires us to negate the second part of the biconditional over here, or actually to negate both sides of the biconditional. Okay, so I got to make sure I discharge this formula, and we're looking for contradictions again, and we see that there are no contradictions. R, S, K, R, no contradiction. But over here we have not R, right? And we have R. So this actually is a contradiction. And because it's a contradiction, we close this branch by writing an X underneath. And what this is telling us is that this particular branch, which is essentially equivalent to a particular line on the truth table, necessarily has to be false. Because in this case, it asserts the truth of both not R and R, and that's a necessary falsehood. However, remember, we only conclude that an argument is valid if it's impossible for the premises to be true and the conclusion false, and that means that every branch has to close. So the branch on the left is still open, and that's because it's not the case that K, if and only if S, can still be further decomposed according to the rule for negated biconditional, which again you'll just have had to memorize. So that's the branching rule, and it goes to K not S and not K S. And having decomposed that rule, I must put a check by it. Remember, always put the checks on the left-hand side. And now, actually, there is nothing more to do except to check whether these remaining two branches contain a contradiction. Okay, so when you check for a contradiction, you only go up, right? This is the branch, so not S, K, not K if and only if S, R, S, K, etc. And I detect a contradiction here. Not S contradicts S, so that closes. And then I go over here, S, not K, R, S, K. K and not K contradict each other. So every branch closes. So since every branch closes, what do we conclude? We conclude that this is a valid argument. Why is it a valid argument? All branches close. Now you'll have noticed in this one that every time we produced a contradiction, it turned out to be between atomic propositions. So up on top, R contradicted not R, not S contradicted S, not K contradicted K. And you might be led to think that that's the way it has to be. But as I explained over here in the upper left, that's not the way it has to be. A contradiction between two can be between any two formulas. So you can have two quite large formulas contradicting each other as long as one is simply a negation of the other. Okay, so that's kind of the basics of argument evaluation for refutation trees. So I'll do the next 5, and I'll start speeding up the process with fewer explanations. So in number 2, we have as a premise, if J then T, and if T then J, which you'll probably recognize as the expanded form of the biconditional J if and only if T, or vice versa. And the conclusion is it's not the case that J if and only if t. So if it's not the case that j if and only if t, then k. Okay? Now you'll remember that the method requires us to negate the conclusion, and hopefully you see that if we simply wrote a negation here, that would not negate the conclusion because this conclusion has been written without the outermost parentheses. The conditional was the main operator, so you had to have added these first. So if you had simply negated it, that would have been wrong, and if you had simply removed the existing negation, that would have been wrong too. The only thing that succeeds in negating the conclusion is this. Okay, so this leaves us with a conjunction and a negated conditional. Those are both non-branching, so you can pick whichever you want. If we pick the first one, we get if j, then t, and if t, then j. Check. Both of these conditionals, both of these are conditionals, and conditionals are branching, so we want to avoid those for now because we have a non-branching formula, and that's going to go to it's not the case that j if and only if t, and not k. Check. Okay, it's okay if that wasn't obvious to you that that's how we decompose that, but it's only okay for a little while because it means you haven't quite memorized this rule. So it's not the case that if A then B goes to A and not B. So in this case, it's not the case that J if and only if T is your A and K is your B, and you have to negate that. Okay, so the remaining rules are all branching. We have J, if J then T, if T then J, and it's not the case that J if and only if T. You can take your pick technically, but the more you do this, the more you'll be able to look a little bit deeper into what's going to occur. You can see that K does not even exist in any of these formulas, so you're not going to get any contradiction out of K. It's just sitting there doing nothing. So when you decompose a biconditional, a branching biconditional, you get sort of more bang for your buck. You get more information, which means more possibilities of contradiction. So although it really doesn't matter, my choice would be to negate the biconditional here. Decompose the biconditional, and what I mean is decompose the negated biconditional. Okay, so this is branching, and this, applying this rule, goes to J not T and not J T. Check. And you'll see, just as we observed, that there's no opportunity for contradiction yet. We have two more open or undischarged formulas now, if J then T, if T then J. And now because there's two open branches below, we have to decompose whichever one we choose under both branch. So that's the new little wrinkle, but it's just following the basic rules. So let's go ahead and start with if J then T. So that's going to go to not J T, right? And then we do it again, not J branch or T, not J or T, not J or T, and check. Now look for contradictions. We've got not J contradicting J. We've got T contradicting not T. We've got not J contradicting nothing. But we've got T, and we've got T contradicting nothing either. Okay, so then we just go back to our last undischarged formula, if T then J. And again, it has to be under both of these open branches. So not T or J, not T or J. Check for contradiction. We have not T contradicting T. We have J contradicting not J. We have not T contradicting T. We have J contradicting not J. Every single branch closed, so valid all branches closed. Okay? Of course, one of the hazards of my doing this here all by myself without you guys in front of me is you're not pointing out my mistakes. So hopefully I'm not making any, but eventually I will, and I'll have to come back and annotate the video to point out where. All right, so the next problem gives us three premises, K and M, if K then P, if M then R, and it gives us the conclusion, P if and only if R, which we have to negate. Okay, now at this point, and for the rest of the video, you really should just be stopping right here and doing it on your own and checking, assuming that you haven't completed all of these already. If you have, congratulations. Hopefully you're just checking to make sure you did everything correctly. So because you have choices in terms of what to decompose, even when you're following the prudential rule with respect to branching and non-branching, my trees are often going to look different than yours, but they will be different in unimportant respects. Okay, so I've got only one branching or non-branching rule here, K and M, so bang, check, right? Then, like I said, very often when I'm given a choice to decompose a biconditional or a negated biconditional rather than some other branching rule, I'll go for the biconditional or negated biconditional because I get more information out of those, and more information means more opportunities for contradiction. So it's not the case that P if and only if R is going to take me to P not R and not P R, check. Okay, no contradiction yet. I've got two conditionals left. Got to decompose them under both. So if K then P, I'll just choose that. Goes to not K or P and not K or P. Immediately check. Not K contradicts K. P contradicts nothing. Not K contradicts K. Way up there on top. P contradicts not P. So see how important it is to check for contradictions at each stage. If you don't do this, you're going to miss some, and that doesn't mean you can't catch them later, but it means your trees are going to get unnecessarily big. Okay, and then we have, finally, we have if M then R, and I only now have to decompose that under the remaining open branch, and that's going to go to not M or R, check, right? So not M contradicts M up here, and R contradicts not R here. So there again we have all branches closing. You might be under the impression now that this is like more common than not. It's not. These are just the ones that we're encountering early. So again, valid, all branches close. So the next one, there's one premise, S if and only if M. Conclusion is not the case that F if and only if not M. It's missing some parentheses. That's how we negate it. Both are branching formulas, so take your pick. I'll just pick the top one. So S, M, not S, not M, check. Okay. And now I go to the next one. That's a negated biconditional, and don't get confused by the fact that the formulas in the conditional are both negated. You just treat one as A and one as B, right? So here we've two, got to do it under both because there were no contradictions found earlier, okay? And we're going to be decomposing this formula in the same way under both. So this goes to not S, which is A, and not M, which is negated B, right? And then we have negated A, which is not S, and not M. And we do this under both. So not S, not M, and not S, and not M. And check. Now let me just point out that don't jump the gun on checking for contradictions until you're actually done discharging the formula. So don't think that it's okay to just discharge under the left-hand side and not the right. Check for contradictions, find that there is no contradiction, and end the proof by calling it invalid. Once you started to discharge something, you have to discharge it all the way. Okay, but there is nothing. Now, are actually a couple of double negated propositions here, so we still have things to operate on, the double negation rule, but we don't necessarily have to operate on them if we get a contradiction first. So here we have contradiction of not S with S, so check. Here we have a contradiction of not M and M, so check. Here we have a contradiction with not M and not M. So even though not M is not fully decomposed, right, we do have a contradiction. So we don't have to decompose not M. And then we have not S contradicting not S. So this too is valid. All branches closed. Okay, the next one says it's not the case that L or M if and only if it's not the case that K or R. And the conclusion is that if it's not the case that not L and not M, then K and R. So we negate the conclusion, right? How do we do it? Where's the main operator? The main operator is here, which means that those brackets have been dropped, and we do it like this. Okay, so now we have a negated conditional and we have a biconditional. The negated conditional is non-branching, so we do that first. So this goes to it's not the case that not L and not M, right? That's the whole first subformula. And not, right, we negate the consequent, right? That's just what the rule requires us to do. And we check. So these are both negated conjunctions. Negated conjunctions are both branching. The biconditional on top is also branching. This one is sort of more labor intensive, or looks like it'll be more labor intensive than the others. But let's just go ahead and see. So I'm going to go ahead and choose to do the biconditional first. So remember, this is a biconditional, not a negated biconditional. So I'm going to try to give myself a lot of room here. So not the case that L or M, and not the case that K or R over here, and same thing over here. Oops, not the same thing, excuse me. We have not L or M, and not K or R, right? So A, B, not A, not B. And check. Okay, so now we have negated disjunctions down here, and those are non-branching. So let's go ahead and just lay those out. So we're going to get a string, not. So we've got not L, not M, check. And we've got not K, not R, check. And we could, if we wanted to, just continue working on this branch by decomposing one of these two remaining formulas, but we'd have to do it under both branches, of course. So I'm inclined to go over here and look at the right-hand side, and here you've got double negation, so this is going to go to L or M, right? Check, and K or R, check. Okay, so these were, and these are of course going to decompose to branching formulas. These here decompose to non-branching formulas. And then you can just sort of take your pick with what you want to do here. You could just choose not K and R, which I'll do. So not K and R goes to not K. And give myself a little more space here. Actually, on second thought, maybe I'll go for the first one. Looks like I might get a little bit more pleasure out of that. So it's not the case that not L and not M goes to not L and not M. And I have to do it here too, right? So not L or not M, check. And here not L contradicts not L, and not M contradicts not M. So we're done with this side. No contradictions over here. We've got three remaining formulas to operate on. So let's go ahead and look at any one you like. So let's go ahead and go to the top, not K and R, just to take care of that one. So that's going to go to not K, not R, and we have to do it here too. So not K, not R, R, and check. And so now there's two remaining branches, L or M, or two remaining formulas, L or M, K or R. So we go to either one, L, M, L, M, got to do it under all of them, right? L, M, L, M, that's a lot. L does not contradict anything, not L and L are just the same. M does not contradict anything. Again, L does not, no contradiction here. L, nope, M, not M. L, nope, M, not M. So no contradictions achieved here at all. Forgot to discharge here. Okay, and so the remaining one is K or R, which we have to do 1, 2, 3, 4, 5, 6, 7, 8 times, right? So K, R, 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 and K, R. Finally, check. Now, if I had been behaving a little bit more intelligently here, I would have gone ahead and double negate and applied the double negation rule to both not L and not M early on, because if these don't close, if any of these don't close, I'm going to have to go ahead and apply this rule to all of those branches. So what I'm going to do is just sort of go back and cheat a little bit, and I'm going to do this retroactively. It's not cheating, I'm just fixing the tree. So let me erase this here, give me a little bit more room. So L, check, M, check. And then we just put our branches back. Okay, so now we are done except for checking for contradictions. So let's look. We got K, not K. Yep. R. Oh, there's no contradiction for R. Okay, R, L, not K. Right, so there is no R, L, not K, L. No contradiction all the way up. So I'm going to indicate that with a circle. And so now, at this point, provided that I've done everything right, I actually don't have to go any further, because this one single branch that doesn't contain a contradiction shows that it is possible for the premises to be true and the conclusion false. How does it show that? Because it shows a fully decomposed branch of the tree that doesn't involve a contradiction. Okay? So this one branch says, oh, here is an interpretation that does not involve a contradiction. So I actually don't have to go check any more of these. I had to fully decompose this rule, but I don't need to check anymore because I have already found my one interpretation that involves no contradiction. Now you can go ahead and check these. We've got K, not K, R, M, not K. So here, again, we have no contradiction, so it looks like there's going to be plenty. So here is a case we're going to say invalid, right? And we'll say at least one fully decomposed branch does not close. Okay? All right, so the last one on this homework, the last one for argument evaluation, gives us a premise R or T. Another premise, it's not the case that not S or not K. Not K. And we have a conclusion, if not R, then T, if and only if S and K. Okay, that's the conclusion, but we need to negate that conclusion, so throw on the outermost brackets, negate it, and we go to town. Go ahead and try it on your own, of course. RRT branching, not the case that not S or not K, non-branching. I'm going to go ahead and do that first. Not S, not K. Discharge, go ahead and take those to S and K right away to avoid any embarrassment from my previous, like in my previous proof. Okay, the negated conclusion is also non-branching, so that's going to go to not R, and it's going to go to T, not the case that T, if and only if S and K, and check. Now we are left with two branching formulas that have not been discharged, R or T, and this one on the bottom, the negated biconditional. I'm going to go ahead and do R or T first here because it's just so obvious to me that I'm going to get some value out of it. R, T, R contradicts not R, so check, and I'm only left with this one. So now I have the negated biconditional. So how does the negated biconditional work? Well, that goes to T, not the case that S and K, and not T and S and K. Check, and hopefully you caught that I forgot to discharge my R or T, so I'm doing that now. That's evil. Contradictions, no, not here, but yes here, T and not T. So we're left with just one open branch. That goes to not S or not K, not S or not K, and check. Oops, that's an ugly check. Okay, check. So not S. Follow that all the way up to S. That's a contradiction. Not K. Follow that all the way up and we get K. That's a contradiction. Valid. All branches close. So once again, notice that I was able to close out this last branch, even though I never decomposed S and K. That's going to be quite common. Sometimes you'll even find arguments where you don't even decompose some of the original premises to demonstrate validity. That will never happen to demonstrate invalidity, however, because when you do invalidity, to actually conclude that an argument is invalid, you have to fully decompose the tree. Okay, I'm going to do the second half of this homework on another video.